Very good. What do we apply here?
X plus 4.
Okay, then what has to happen to x plus 4 for log to be applied to x plus 4?
See previous.
See previous, thank you. So then I have a system of two inequalities that I need to solve. The first one clearly says greater than -3, the second one greater than -4. So therefore now I need to find the common territory. So remember, I don't care for units here. This is just to help us find the common domain. So here's -3 to infinity. And here's -4 to infinity. I have to choose the territory that makes both functions exist at the same time. So the common domain is? Thank you very much. Excellent. Perfect explanation, perfect answer. Thank you. So then, I know that if, when I solve this equation, if I get the solution as x equals -5, what would you say? Acceptable or not?
No.
No. What if I get a solution as x equals 10? Acceptable or not?
Yes.
Yes, agreed. Very good. So let's look at this. And please tell me, how do I condense the left-hand side?
Log base 6 of
Yes?
So then you so that's x plus 3 times x plus 4.
Awesome. Great. This is indeed log applied to a product is the sum of logs. Sum of logs converted back to log applied to a product. Awesome. Only now I can change this into an exponential equation.
6 to the first power.
6 to the first power, exactly, equals this. I'm going to distribute it. So it's x squared plus 4x plus 3x plus 12. One more time, so please watch. 6 raised to the first power equals this. And this product is here. Good. What type of equation is this now?
Oh, I was stretching actually. But
That's okay.
that is quadratic.
Very good. What do I have to do in order to solve a quadratic equation?
Factor.
At this stage?
Oh, combine like terms.
Good. So I have x squared and then plus 7x.
Plus 12.
Careful.
Minus 9 plus 6.
Very good. When I solve a quadratic equation, I have to have it set equal to 0. Good. And then what will be the next step?
Factor.
Yes. I'm ready when you are.
X plus 6, x plus 1.
Good. So there are two possibilities for x.
-1 and -6.
So what do I conclude?
You go up a little bit.
No, just kidding.
Can't be 1 because if you plug negative, well, it can't be -1 because if you plug that back in, it doesn't equal 0.
Well, I don't think it could be -6. That's not another one.
Well, in that case, it has no solutions.
Well,
-6 is not in this interval. I agree. This is not. What about -1?
Is.
Yes. So the only solution is x equals -1. Any questions? Any questions?
6.
If you're checking these two here, they both work. We're not checking them in here. We're checking them in the original problem.
I see, okay.
So
Yeah, you're taking
these two
that.
will always work here. Of course they will, right? But they will not work here. Look, -6. Negative 6 plus 3 is negative 3. You cannot apply log to negative 3. Now, when we check negative 1 plus 3 is 2. I can apply log base 6 to 2. Negative 1 plus 6 plus 4 is 3. I can apply log base 6 to 3. Okay, very good. Okay, let's look at another example.
Question.
Yes.
Exponential function, domain is all real numbers.
That's why we haven't even mentioned.
Range is 0 to infinity.
Correct.
And then for the inverse of that function, which is a logarithmic equation,
The domain is 0 to infinity.
so the domain is 0 to infinity, and then range is all real numbers.
Correct.
Yep.
Okay.
Correct. That's why.
Swapping the range of the
Yes.
domain.
That's why we graphed them at the beginning to refresh your memory.
Right.
As you see, domain, all real numbers, range 0 to infinity.
Okay.
Reverse, domain, 0 to infinity, range, all real numbers.
Looks good.
No matter which shape, they both fulfill the same conditions. Very good. Okay, so let's look at another log. Yes, let's look at 76. And we have log base 2 of x minus 3 plus log base 2 of x minus log base 2 of x plus 2 equals 2. Okay. What type of equation is this? Definitely logarithmic, base 2, very good. Can anyone give us the domain of this function, or not the domain, but just what I should write? Awesome. For this one,
X is greater than 0.
awesome. For this one,
X plus 2 is greater than 0.
very good. So we stated restrictions, and please remember the restrictions have to be stated before you condense. Because if you condense, the domain will not be the same. Be very careful. You have to state the restrictions on the raw equation. Good. So I'm solving this, x greater than 3. I'm solving this, x greater than 0. I'm solving this, x greater than negative 2. I'll try to find the common territory, the common domain. Greater than 3. Greater than 0. And greater than negative 2. I have to choose the common territory to all three, where all three logs will exist. So the common domain is, thank you. Very good. So if I don't find a solution greater than 3, I'll say no solutions and I'm done. Good. So now can anyone tell us how to condense into one log? I want one log on the left-hand side, base 2, and on the other side I only want 2.
X minus 3 times x over x plus 2.
Very good. Because we discussed this, right? If the log has minus in front, its expression is coming from the denominator. If the log has plus in front, its expression is coming from the top. Very good. Now I can change this into an exponential equation. How do I do that? Yes?
And then to the second power,
2 squared equals
the
x squared minus 3x over x plus 2. Very good. So 2 squared equals that entire expression. Very good.
choose the base, but what do you call that thing with the parentheses, the x?
The number I apply log to. The expression I
That's
apply
what it's
log to.
called?
Yeah, it doesn't have a name.
Okay.
It's the expression I apply log base 2 to.
Got
It's what I apply the function to.
Normally you could call it the exponent, but in this case, because it's a difference, you can't.
No, the exponent is 2.
Really?
Yeah, 2.
2 raised to the second power.
equals
2 raised
Okay.
squared is all this.
Right.
Good. Okay, so then I have 4 to the left on the left-hand side, then x squared minus 3x over x plus 2. So let's look at the big picture now and identify this equation. What type of equation is this?
Oh, then you call it the argument, don't you?
If you want, yes.
That's just how I was taught.
Correct. I completely agree with that.
But yeah,
So what type of equation is this?
rational?
Yes. Here's your hint. And then what do I do? I put the hint for you. Exactly. So 4x plus 8 equals x squared minus 3x. Now I'm asking you again, what type of equation is this?
Quadratic.
Quadratic. How do I solve it? X squared, I move everything to one side, set it equal to 0. X squared minus 7x minus 8. I moved 4x and I moved 8. Okay, so what do I do with x squared minus 7x minus 8?
-7, -1. Right, -7 and 1, or 1 and -7.
negative positive 1.
Very good. So x equals
+8, -1.
perfect. So now I'm going back. I'm digging deep. And what will I conclude?
Only x equals 8.
Very good. Is the idea clear with concerning log equations? We will have to practice more, of course.
Another thing to remember is find the restrictions before you condense it.
Yes.
Expand it more. Okay.
Yes, because when you state restrictions after you condense, the domain will be different.
Got you, right.
Good. And the last section of this chapter deals with applications. So this is 4.5, applications.
Like this is the last one in chapter 4.
The last one in chapter 4, and then we will look at systems of linear equations in 2 variables, 3 variables, and matrices. Yes, there is. Okay, applications. There are basically 3 different groups here. Group 1, exponential growth model. The exponential growth model is for populations, is for mice, rats, fish, bats,
People?
Yes, people. So the exponential growth model, normally we don't use the notation in our book, but I'll show you both. We say n, this is n, number of time t, is the number n0 e to rt.
That's continuous growth, right?
Yes. The exponential growth model is continuous, a continuous function. However, your book uses a, not a of t, which I disagree with, uses a0, which is the number initial, that's fine, and they use e to kt, that's fine too. It doesn't matter, as you see, it's the same thing. So I think this notation is more useful, but we are going to use both, it doesn't matter to me. So the number of bacteria grow exponentially. The number of people, the number of fish in the pond, the number of bats, mice, rabbits, or the value, the accumulated value. I don't know why we would use A, but that's what they use. These are the initial values, the initial population. Initial initial number of bacteria, initial number of fish, initial number of mice, initial number of people in a city. And E, of course, is our friend Euler's number. And R or K, it doesn't matter. So R or K, growth rate. And T is time. It could be in hours, in minutes, depending if we talk about bacteria, it may be seconds, it may be hours. If we talk about mice, it may be months, maybe years, I don't know.
N to the 0 has to be greater than 1, right?
Yes,
Or
of
else
course.
there's no
It
possibility
makes no
of growth.
sense, of
Okay.
course, of course. The second model is the exponential decay.
This chair gets real squeaky, it is.
The exponential decay model. And you will see the difference. We talk about exponential decay when we talk about radioactive substances. And when we talk about radioactive substances, we talk about mass, not number, but mass. So the usual model is m of t, mass of t, m0, the initial mass, e to minus rt.
Well, technically, very quick tangent here. Sometimes, like in the case of Avogadro's number, sometimes the mass corresponds to the number of atoms. In fact, I think it always does. It's just a matter of what number it is. But yeah,
I have to see the relationship, however.
yeah.
Once we look at the relationship, we'll be able to, most probably, we'll be able to figure out what it was meant
Yeah.
with m. Because it could be the number of moles. It doesn't have to be mass.
Yeah.
So we have to look carefully.
Mhm.
Okay, so your book doesn't like this, of course. They use this. It's all the same. It's still, this is the initial mass of substance. This is still the initial mass of substance. R is still the exponential decay rate, and K is still the exponential decay rate, all the same. And the last one, oh, by the way, you do not have to memorize any of this. The exponential growth model will be given to you in problems. The exponential decay model will be given to you in problems. You do not have to memorize any of this. Now, if you remember, we already looked at this, which made sense, which was the accumulated value t years from today when we, I didn't use A0, I used P. Yes. So principal, E, R, T, annual interest rate, time in years.
No, why? I have a question.
Yes.
Why is 1 plus the rate over time
Because that was for the
equal
compounded.
to E equals?
This was for continuous
Yeah, well,
compounding
E is-
interest.
Okay, so continuous. I mean, like I'm trying to understand like mathematically. I was trying to like see how 365. I mean, the rate over 365. How that correlates to like continuous
No, continuous means every second.
Okay.
365 means the interest is compounded every day.
Okay, got you. Okay.
So if you're thinking of this formula, so this is A of t, which is P1 plus R over N raised to NT. Yes,
Yeah.
I agree. But this, if this is 365,
Right.
then they are compounding interest 365 a year.
Okay.
But this one does not have any number of, it's compounded every second,
Instantaneously.
instantaneous.
Okay.
Now,
Okay.
Now, you may have some idea, which I think we are probably thinking of this. If this is $1,000, for example, and this is $1,000, and you put 365 and 365 and continuous, the difference, depending on the number of years, if you say, okay, 4 years, the difference may be
So it's,
not even pennies.
got you. It's very, very
Right.
minuscule difference.
Right.
But,
But if this is $1 million, and you're looking at 50 years,
so,
the-
okay, this
I
is
haven't
very-
calculated anything, but I'm saying the difference could be significant.
E is way more precise though than.
So I don't know. I have to look at it.
Okay, that makes sense.
And the last one that, again, you do not have to memorize is logistic growth model. I don't have a specific formula. They're all different here. So I'm going to start with a problem like this so you see. So there is not one particular logistic model. There is a generic one, but I will have to use letters in it. So you don't have to memorize. I can show it to you in the book. Here it is. Logistic growth model. It looks like this. A number C at the top, 1 plus another number A, e to negative bt. This is not important. Nobody will test you on that. Okay. So I want to start with a problem like 37. On page 530. The logistic growth function, f of t, equals 100,000 divided by 1 plus 5,000 e to negative t. And we're asked, number one, first of all, the description. This describes a number of people. Number of people. F of t, who have become ill with influenza T weeks after its initial outbreak in a particular community. So T in weeks. Okay. First question. How many people became ill with the flu when the epidemic began? How many became ill with the flu when the epidemic began? What am I really asked to find? Very good. We'll determine it in a minute. Part B. How many people were ill by the end of the 4th week?
F of 0. No, 4. Why did I say?
Good. So let's plug it in y equals. Clear if you have anything in there. 100,000 divided by, in parentheses, 1 plus 5,000 times e. Here's e to negative x. Close the parenthesis. I need to put parentheses here. If you're confident that your calculator doesn't need it, then you don't have to put them in. And second in table, let's discover what I did, what it does not like.
Maybe the parentheses in the exponent.
It shouldn't. Okay. So second in table. And we want 0, which we already have. And we want 4. Okay. So for 0, 20 and 1,080. Okay, here's the next question, final question here. What is the limiting size of the population that becomes ill? Meaning, what is the maximum possible?
100,000.
How do I know that? It just spoiled my... I wanted to build it up.
I just figure that's the total population, right?
How do you know that?
I don't.
Okay.
Truthfully.
Okay. Thank you, Tom. Okay. So how do I think about the limiting size of the population. Okay, so we know that initially 20 people were sick, and then 4 weeks later 1,080 were sick, and then 6 weeks later I don't know how many, definitely more, and then 10 weeks later more, and then 12 weeks later more and more and more and more and more, right? So one way would be to increase the number of weeks and see what happens. Okay, so I'm going to say 12 weeks later, 97,000. Okay, let's say 70 weeks later, 100,000. And then say 80 weeks later, 100,000. And then 800 weeks later, 100,000. So what is the limiting size of the population that could get ill? Not more than what they have.
Yeah.
So what type of concept is this?
A limit?
Yes,
Close enough.
but you're right, it is a limit. Okay, so as x, or the number of weeks increases without bound, the function values get closer and closer, closer and closer to what value?
100,000.
Correct. So indeed, max 100,000 people, since y equals 100,000 is the horizontal asymptote at infinity. Although we cannot really say infinite weeks, number of weeks, but yes. Okay. I would like to look at a problem with exponential growth now. And I'm looking for a problem on page 539. I would like to look at problem 26 on 539. The function a of t equals 82.3 e to negative 0.004 t. Okay, since it's negative, it's an exponential decay. Models the population of Germany, A, in millions. So this is in millions, and T is in years after 2010. T equals years, since 2010. What was the population in Germany in 2010? That's
82.3 million.
I completely agree. So A of 0 is 82.
On there.
Because we know that this quantity is the initial. Good. Okay. Part B. Is the population of Germany increasing or decreasing?
Decreasing.
Yes, I agree because of the negative symbol here. Part B. C. In which year will the population of Germany be 79.1 million? And the question is when? Say it again. Yes, I'm ready. Yes, that's all I needed you to say.
So A times T is 79.1 equals 82.3
Awesome.
times E to the negative 0.004 T.
Very good. Now I'm thinking, I'm looking at this, and I'm asking myself, what type of equation is it?
Exponential.
Awesome. What is the first thing that I have to do? Look at it carefully and say, you cannot proceed before you do blah.
Get rid of 82.3.
Thank you. Thank you. Thank you. So indeed, 79.1 over 82.3 equals e to negative 0.004 t. Awesome. You don't actually have to divide. Just keep it in the fraction form. Okay, so I have cleaned it up. And now I am asking myself again, how do I proceed? What do I need to do? Because obviously, the left-hand side and the right-hand side cannot be presented with the same base. So what is the procedure then?
Let's take things down a level.
Yes, how do I do that?
Well, you have E, so it makes it easy to take the natural log.
Very good. Awesome. Two numbers are equal, their logs will be equal. Awesome. Thank you. So then natural log 79.1 over 82.3 equals negative 0.004t. Final step, I have to solve for t. So let's solve for t. What do I have to do to both sides to solve for t? Both sides by? Very good, thank you.
This is really just multiplying by 400, 4,000.
Only if you multiply top and bottom by 1,000.
Oh, okay.
And then you still have to divide by -4. But there is no need, but yes, you're right. There is no need to do that. So let's go to clear and natural log 79.1 divided by 82.3. Close and divide in parentheses by -0.004. Close. So time t, 9.91 watt. Approximately, yes. Yes.
So pretty soon.
Yep. However, they got a lot of new people helping them with that now. So I'm assuming the model will not be valid anymore. Good. Any questions on the applications of exponential growth or decay, logistic growth model? Do we need more examples? I know we do, so we will have more, but right this moment, definitely we'll have more. But right this moment, would you like us to work on another word problem or move on to systems? Should we choose another word problem? Say it again. Say it again.
Let's move on.
Okay, awesome. Good. I will come back because I know this is 2 or 3 problems are not enough. Okay. Now, let me show you where we are and what we're doing. I'm looking for my handout that I gave you on the first day. Here's where we are right now. I am hoping that all these problems will be done between now and on Thursday, I'm sorry. So you can ask questions, check, maybe there is something that we haven't discussed. So these are extremely important. There is no way I can finish everything, show you every type I want to. So if you find something, anything in there, we'll do it in class together. So right now we are looking at these 2 sections. And there are 3 sections left afterwards. So 5.4, 5.5, systems of nonlinear equations. And this is the last topic of series, sequences and series, section 8.1. So systems of inequalities, nonlinear systems of equations. So we are looking at addition, substitution, and matrices right now. Okay, so we start with 5.1. Nothing in 5.1 should be new. I will be more than happy to show as many problems as you need. However,
This is with like multiple variables, right?
yes, but just 2.
Okay.
Just systems of linear equations and 2 variables in 5.1. So systems of 2 by 2. What does that mean? 2 linear equations in 2 variables. What will 3 by 3 mean?
3 linear equations and 3 variables.
That's it. Okay, so let's practice this with a couple of examples, one with substitution and one with elimination, to refresh our memory on this. If you think that you have forgotten the systems or the method, let me know and we'll do more problems. Let's say problem 14. And this is on page 555. 2x plus 5y equals 1, and negative x plus 6y equals 8. Okay, so I see two equations, I see two variables, and let's suppose the problem is asking us to use substitution to solve the system. If I'm asked to use substitution, so substitution, I will first look at the four different coefficients. I see coefficient 2, I see coefficient 5, I see coefficient -1, and I see coefficient 6. The only variable that I would think of substituting for is only this one. If I try to solve the first equation for x, I will have to divide eventually by 2. No. If I want to solve this for y, I will eventually have to divide by 5. No. If I solve for this y, I will have to eventually divide by 6. No, not a good idea. This is the only one, because division by -1 will not create a fraction. So I will solve the second equation for negative x first, copying the first equation as is. Just copy it, 2x plus 5y equals 1. And here I will move 6y, so negative x equals negative 6y plus 8. Now the final step for the second equation is to multiply or divide both sides by -1, which is friendly, not a problem. I will copy the first equation again and multiply the second one both sides by -1. So I solved the second equation for x because I'm asked to use substitution. So now in the first equation, I can replace this x by this. And I created an equation with only one variable. By simply replacing x by this quantity, why? Because they are the same, I will create a new equation which is twice in parentheses 6y minus 18 plus 5y equals 1. Since no one can see it right there, forgive me, I'm going to write it again. 2, 6y minus 18 plus 5y equals 1. Now this is an equation in only one variable. I know how to solve this. It's linear. I distribute, combine like terms, move terms around, and it's done. So 12y minus 36 plus 5y equals 1. 17y equals 37. 2x, 5y. Did I copy everything correctly? Oh, yeah. Sorry. So this is 8, not 18. I don't know how I got that. So 16. Good. Much better. Okay, 6y plus 8, 6y minus 8, correct. That's 12. That's 16. That's 5y, that's 1. That's 17, and that's 17. Okay, so then y equals 1. With y equals 1, I go back, and I determine x. How much is x? Very good. So the solution appears to be -2, +1. I have no idea whether this is true or false, but I will know in a blink. So -2, -2, 1 and 1. 2 times -2, -4. 5 times 1 is 5. 5 minus 4 is 1, yes. -2 with minus in front is 2. 6 times 1 is 6. 2 plus 6 is 8, yes. And now I know that this is indeed the only solution and no one can find another. And this was the method of substitution. Do we remember the method of substitution? Yes? Okay, perfect. So now let's look at one with elimination. If you want to choose, I'll work on the problem you want. If not, I will choose. Okay, so I will choose, say, 28. In 28, we have 2x plus 3y equals negative 16, and 5x minus 10y equals 30. This problem is asking us to use elimination. I know that you know a little bit about me. And one of the things that I enjoy doing very much, and it's always in the back of my mind, is simplify and factor. Always. There is nothing I can do to 2x, 3y, and negative 16. I have no choice there. It has to stay. But 5, negative 10, and 30, no. Here I can impose a division by 5. So I have 2x plus 3y equals negative 16, and an x minus 2y equals 6. This is a much easier situation now. Why? Why did I do that? For many reasons. But here's one main reason. If I were to eliminate without simplifying, I would have had to multiply both equations by a quantity. So in order to eliminate x, I would have had to multiply this by 5 and this by negative 2. If I wanted to eliminate y, I would have had to multiply this by 10 and this by 3. So both equations. But getting rid of 5 and simplifying the second equation, now it's clear what I'm going to do. I'm not going to eliminate y because I have to multiply both equations. But I'm going to multiply only the second one by negative 2 so that I can eliminate x.
Is that for simplicity or also for accuracy?
Sure, sure. No, it's the same.
It'll be the same thing.
Oh,
but it's
absolutely.
simple.
If I find the correct solution, you cannot find another.
Okay.
If you find the correct solution, I will not be able to find another. All these systems, maybe I should have refreshed the memory on that. All these systems of 2 by 2 have only 3 possibilities. One possibility is when the two lines meet in one point and one point only. If you find the correct solution, there is no way I can find another. The second option is no intersection whatsoever. The system has no solutions. And there is a third one. Infinitely many solutions.
Are they both the same line?
Exactly. Exactly. They're hidden in the sense that one is, they're given as 2 different lines, but actually they do represent the same one. Okay? So then, in order to eliminate, I'm going to multiply the second one by negative 2. Copy the first equation, 2x plus 3y equals negative 16. And negative 2x plus 4y equals negative 12. And now I'm eliminating or adding. So some books call this method the elimination method because I'm eliminating one of the variables. And other books call it the adding method, whatever you prefer. So I'm adding. So obviously I divide by 7, so y equals negative 4. Is this enough? No, it's not enough because I have to go back and replace y so that I can get x. So x plus 8 equals 6. So therefore x equals negative 2. So what is the prospect solution that I'm not sure of yet because I haven't checked. And I don't need anyone to tell me whether.
Negative 2, negative 4.
Negative 2, negative 4. So I go back now to the original problem and check. Negative 2, negative 2, negative 4, negative 4. 2 times negative 2, negative 4. 3 times -4, -12. Yes. -10 plus 40, 30. Yes. So I will say definitely yes, and no one can find another. So if I found a solution and it works in the system, assuming I didn't make mistakes by plugging it in, then no one else can find another. Because it's definitely not the case of the overlap. Okay. The next section that we have to look at is 6.1. And I just want to start it. We're probably not going to be able to go through a complete problem. Matrices. So of course, the title is Solving Systems Using Matrices. Solving systems of 3 by 3 using matrices. Solving systems of 3 by 3 using matrices. I just want to copy a problem like problem 29 on page 631. So what is this? It's a different method, similar to substitution, similar to elimination, but for systems that are more involving than a 2 by 2. 3 by 3, of course, requires more work than a 2 by 2. Okay, so here's the system. X plus 2y equals z minus 1. X equals 4 plus y minus z. And x plus y minus 3z equals -2. So let's look at the system. Let's analyze what it means and what it says to us. So what is it?
There's 3 axes.
So 3 variables and 3 equations, correct? I claim that I don't like the way it is presented to us. Why do you think I claim that? Look at it.
Is it not in X, Y, Z order?
Of course. Everything has to be in the correct order. So please dictate.
X plus 2y minus z plus equals -1.
Very good.
Negative x. Oh, x equals, no. X minus y plus z equals 4.
Awesome. And the last one is friendly. I just need to copy it. Good. So now the system makes sense. I see variables with x, one below the other, y one below the other, z below the z, and the equal symbol and the free term. Good. At this point, we have to identify a couple of ideas here. A is a matrix. And you can see, what is a matrix? I'll explain in 1 second what a matrix is. A matrix of coefficients. Meaning, not variables, just coefficients. So here it is. A equals so it's an array of numbers. Array of numbers consisting of the first column will be the coefficients of x, 1, 1, 1. Now you understand why this needed to be in this particular order. Can anyone dictate the coefficients for y? Very good. 2, -1, 1. Perfect. And for z?
-1, 1. 3, negative 3.
Yes, good. So we established the matrix of the coefficients of the system. Good. Now what it's called the augmented matrix. The augmented matrix is different. The augmented matrix looks like this. A vertical bar, lowercase b. I'll explain in a minute. Put them in brackets. And again, open brackets again on the right-hand side, so we present what this means. This vertical bar will be right here as well, represented. The lowercase b are just the free terms, -1, 4, -2. And the rest, I copy the matrix in here. 1, 1, 1, 2, -1, 1, -1, 1, -3. Okay, let's stop for a moment and discuss what we just did. We were given a system. It's a 3 by 3 system. It was not arranged in the proper order. We rearranged it. Step number 2. We created the matrix of coefficients. The matrix of coefficients is this. The next step, using the matrix of the system and the free terms from the system, -1, 4, -2, we created something else that it's called the augmented matrix. It's the matrix with another column next to it, augmented by the other column, the last column. Okay. So now, how do I solve the system? What is the idea? So here's the idea. We will go through different steps. I'll explain the steps in a moment. And if at the very end, when I can say I solved the system, I have to show you something like this. Don't say anything, just let me just implement the idea and then we'll talk about it. If I manage to change that augmented matrix through some steps, some miracle steps, and I change it into this, but I have to show you how I get here, right? I haven't showed you how. And if I get to this, can you tell me how much is x? X plus 0 equals A. Can you tell me how much is y?
B.
Can you tell me how much is z?
C.
That's it. What I have to do work between that step and this step. Oh, sweat. Okay? So now let's list the only three steps possible and allowed. We're not going to be able to finish this, but I just want to list those 3 possible steps. I cannot use any trick other than one of these 3. Trick number 1. Swap rows. What does that mean? Here's a question. If in this system I consider this one the first row and this one the second row, will I change the solution of the system?
No.
No. So I'm allowed to do that if I need to. Trick number 2. Multiply or divide both sides of an equation, of any equation in the system by a non-zero number. So here's the question. If I go back to the original system, and if I decide for whatever reason to multiply both sides of this equation by 5, will I change the solution? No. And last one, and then I'll stop.
Any real number that's not 0?
Yes.
Because you know I.
Okay. Of an equation by a non-zero and real.
Just
That,
being a little bit nitpicky.
that does it. Okay, you'll see. I'm gonna hold that against. No, I'm kidding. I'm kidding. I'm kidding.
It's fine.
I'm kidding. You can't make me laugh just yet. I'm not ready for laughter.
Okay.
Sorry about that.
That's fine.
Not your fault. Multiply any row by a non-zero number real and add the result to another row. Multiply any row by a non-zero number and add the result to another row. Or divide, of course. You can say, where does this come from? Here's where it's coming from. We multiplied this row by -2, and then we eventually added it to the first equation to get this. That's where it's coming from. So on Thursday, we're going to finish this problem.